Hello, my name is Tyler Ingerbrand, and I'm going to be presenting the paper Zero-Shot Reinforcement Learning via Function Encoders. So first I'll introduce a useful abstraction, which is Hilbert spaces. In a Hilbert space, any vector f can be represented as a weighted linear combination of basis vectors. Furthermore, the coefficient c can be computed as an inner product between the vector f and the basis vectors g of I. Now this abstraction gives us two useful properties. The first is that given the basis vectors and the coefficients, you can reproduce the vector f, and in a minute we'll see how useful that is. The second property is that because these coefficients can be used to reproduce the vector f, that means they are a fully representative, a fully informative representation of f. And so therefore we can use them as a representation for downstream task. Lastly, the thing to note is that Hilbert spaces can be used to describe a whole bunch of settings. Notably, we'll be talking about function spaces here. To make functions fit into this framework, we're using the typical L2 definitions. Primarily, this means that we compute the coefficients as an integral over the input space of f of x times g of x. However, crucially, we approximate this integral using a Monte Carlo integration. This approximate integral is extremely quick to compute, as it's basically a sample mean. And so this is a key detail of this paper because you can compute these coefficients extremely quickly online, given just an example data set D. And when you're using functions as the Hilbert space, the weighted combination of basis vectors means that you can predict a function f of x as a weighted combination of the basis vectors. And given that we can compute the coefficients quickly, this means we can do zero-shot online predictions just as a weighted combination of the basis vectors, given some example data. And so in a minute, we'll see how useful that can be for many reinforcement learning settings. One problem, though, is that we need a way of finding the basis functions. Now, there are analytical solutions of good basis functions for any function space. However, these solutions often require a huge number of basis functions for high-dimensional spaces. And so instead, we're going to learn a minimal set of basis functions using neural networks. Here's the algorithm that we introduced to do so. The basic idea is that you initialize neural networks as the basis functions. Now, initially, they don't span the space of interest or do anything useful for your problem, but you sample functions from the space you want to fit it to. And then for each of these functions, you compute its coefficients via the inner product. You reproduce the function as a weighted combination of the basis vectors, and then you measure the loss between that function and your reproduced approximation. And then you simply minimize that loss, and after training for a few iterations, you get basis functions which span the space of interest. Now, you can apply this algorithm to any Hilbert space, and so here I'm demonstrating on Euclidean space just to show you kind of what the algorithm looks like in practice. And as you can see, these black basis vectors are slowly converging to the blue square, which is the function space, or in this case, just a plane that we're trying to fit to. Now, the way you use this algorithm in practice, you first have to recognize what part of your problem is a function space. Then you collect a large offline training data set of various functions from this function space, and you use that to train the basis functions via the function encoder algorithm. Once you have those basis functions, you can use them for online prediction. So you use that approximated inner product to compute the coefficients, and then you can reproduce the function online, and you can do this in only a few milliseconds. The other thing you can do is use those coefficients as a context representation for downstream tasks, such as reinforcement learning. So the first example I'll look at is dynamics predictions for hidden parameter MDPs. So in hidden parameter MDPs, there is a hidden parameter every episode that is fixed for the episode, but affects the dynamics. And so the problem is, how can you accurately approximate the dynamics given that there's a hidden parameter you will never have knowledge of? And so the key is to recognize that each episode you get a hidden parameter, and this is effectively fixing the transition function from a space of transition functions. And so you can train a function encoder to learn the basis over this space of transition functions. Then, given some online data, say the first few steps of an episode, you can use that data to compute the representation via that inner product, and then you can approximate dynamics as a weighted combination of basis functions going forward. And crucially, this never uses knowledge of the hidden parameters, it only requires data. And so here we're comparing this approach, marked in blue, against other approaches. Notably, the function encoder approach is outperforming the transformer. Interestingly, it even outperforms an oracle, which is given access to the hidden parameters as an additional input, which suggests that the inductive bias of a linear combination of basis functions is quite good for learning in this setting. Another thing is we can look at the representation space with respect to a change in hidden parameter. And we see that we get this nice smooth color gradient. So a small change in a hidden parameter leads to a small change in the representation. And this suggests that for any downstream task, this representation would be really easy to work with because it is sort of smooth and consistent. Another problem we can apply this to is multitask reinforcement learning. So in multitask RL, the agent's trying to maximize reward, but the reward function is sampled from a space of reward functions every episode. And so the problem is, how can we learn one policy which achieves good reward for any reward function? And furthermore, a lot of reward functions will be quite similar. And so another thing is, how can we reuse policies from similar reward functions so that we have to learn less? The solution is to first train basis functions over the space of reward functions. Then for any new reward function, given some data on it, you can compute its representation via that inner product. Once we have the representation, since we know it's fully informative of the reward function, and it's got some nice smooth and linear properties, we can just simply pass it in as an additional context variable to the reinforcement learning algorithm. In practice, this just means you pass it in as an additional input to the policy and value functions. And due to the linearity of the representation space, this means that similar reward functions will have similar representations, and therefore they will have similar policies, as the neural networks we're using are inherently continuous. And so here we can see on this Miss Pacman example that the DQN algorithm, which is simply using the function encoder task representation, is able to outperform other methods. And again, we can look at the representation space with respect to a change in reward function. And once again, we see that the function encoder has this nice smooth change in representation for different goal locations, whereas some other algorithms do not necessarily get this property. Interestingly, transformers also, in this case, happen to learn a good representation, which probably helped explain why transformers also perform quite well on this problem setting. The last example I want to talk about is multi-agent reinforcement learning. In this setting, it's a two-player game, and every episode, a new adversary is sampled from a set of adversaries. And so the goal is that the ego agent should perform well against every adversary. And the question is, how can we find an optimal policy against each adversary, and how can we exploit each adversary specifically? The solution is to recognize that the space of adversary policies forms a function space. And so we train basis functions over the space using the function encoder algorithm. And then for each adversary, given a small amount of data on how that adversary performs, we can compute a representation. And then once again, we simply condition the reinforcement learning algorithm on the representation of the adversary. And so this is basically a fully informative description of the adversary that the RL algorithm can then use to exploit that adversary. And here we see that by augmenting PPO with a function encoder task representation, we get improved asymptotic performance and training stability relative to other approaches. And interestingly, in this case, the transformer performs terribly, which is largely due to the inherent data-hungry nature of transformers in a setting of multi-agent RL where data is hard to come by. All right, that is the end. Thank you.